Good afternoon. We'll continue further with our lecture on the amorphous form. Today we are going to discuss about the generation of the amorphous form. Before we talk about the techniques that are used for the generation of the amorphous form, we will be talking of a couple of terminologies that are associated with the phenomena of generation of the amorphous form. The first term that we are going to discuss is called as the glass forming ability. As the name indicates, it basically talks about the tendency of a crystalline material to form the glassy material. What is the ability of a crystalline material to form a glass is described by the glass forming ability. It is also defined as the ease of vitrification of undercooled melt upon cooling. Vitrification is nothing but the process of formation of the amorphous state. Glass forming ability is assessed based on minimum cooling rate for glass formation, that is the slowest cooling rate at which the material can be transformed to the amorphous form. And this is called as the critical cooling rate. Now we are basically talking of a protocol that is followed in the differential scanning calorimetry, in which you take a sample in the DSC cell, heat it beyond its melting point, and then you cool it back. So the cooling rate that is required for the formation of the glass, or the minimum cooling rate that is required for the formation of the glass, is called as the critical cooling rate. So the materials which can form the glass at a slower cooling rate would be better glass formers as compared to the material which require a very fast cooling rate for formation of the glass. Thus, glass forms when the critical cooling rate is much greater than the rate of reorientation of the molecules that is required to initiate the crystallization. Thermodynamically, higher glass forming ability originates from a crystalline state that is not substantially stable than the amorphous state. In other words, when the free energy difference between the crystalline and the amorphous state is not very large, then the material will have a greater tendency to form a glass. The other term that is used is called as the glass stability. And the materials have been classified into three classes based on their crystallization tendency from the undercooled melt. Undercooled melt is after you have melted a particular sample and then you suddenly cool it so as to bring it into the supercooled liquid state. Class 1 materials do not form glass on cooling and rather crystallize during the cooling run. So we are talking of a DSC protocol wherein you take a crystalline sample, you heat it beyond its melting point, then you cool it back to the room temperature and again heat it to the higher temperature. So we are giving 3 cycles in the DSC, and these are called as heat cool heat protocols, wherein you first heat it beyond the melting point, then you cool it back, and then again you give it a heating cycle. So the class 1 materials do not form glass on cooling and they rather crystallize during the cooling of the melt. Class 2 materials form glass on cooling, but that recrystallizes on the second heating cycle. Class 3 materials have a tendency to form a glass on the cooling and it does not crystallize on the second heating, which means if you look at from the tendency of the stability of the glass, these are the materials whose glass is not formed at all. Class 2, there is a formation of the glass, but it is not very stable because it recrystallizes. And the class 3 materials are good glass formers, plus their glass stability is also higher because they do not recrystallize during the second heating run. These 3 classes are shown pictorially in these 3 diagrams. So this is the picture for the class 1 materials. So what is shown here is that during the cooling, they tend to crystallize. The first heating run has not been shown here. So in the cooling run, they crystallize. So there is a exothermic peak. And then when you give it a second heating run, it directly shows the melting point because it has already converted into the crystalline sample. In the case of class 2 materials, during the cooling run, there is a formation of the glass. So there is this kind of dip here which is seen. And during the heating run, you will first see a glass transition temperature. Later on, you see a exotherm, which is the recrystallization exotherm, which is followed by the melting endotherm. What it means is that although the glass was formed, it converted back into the crystalline sample, or it recrystallized during the second heating run, which then shows you the melting point. This is the example of the class 3 material, which convert to a glass during the cooling run, and in the second heating run, they only show you the glass transition temperature, and subsequently no melting event is shown, which means the glass which is formed remains kind of stable and it does not convert to the crystalline form, and no subsequent melting point is seen. Some of the drugs which fall under these classes are listed out here. Naproxen and theophylline fall under the class 1. Celecoxib and nifedipine are class 2 drugs. Indomethacin and famotidine are class 3 drugs. These are some of the molecular and supramolecular parameters which are related to the glass stability of different materials. So we are going to discuss the two extreme cases, that is the materials that fall under the class 1 and which fall under class 3, because these are the two extremes. Class 1 have the least glass stability and class 3 have the best or the maximum glass stability. If we compare in terms of their molecular weight, the molecular weight of the class 1 compound is lower while that of class 3 is higher, and typically it would be greater than 300 Daltons. The flexibility or the rotatable bonds in the case of class 1 materials are rigid, whereas in the case of class 3 they are flexible. The free energy difference between the amorphous and the crystalline form is higher in the case of class 1, whereas it is lower in the case of class 3. The melting point of class 1 materials is generally higher, while those of class 3 materials is lower. So as we had discussed, if the difference in the free energy of the amorphous form and the crystalline form would be higher, there would be a higher tendency of conversion back to the crystalline form, and in the extreme cases, the amorphous phase would not be formed at all. While if this free energy difference is lower, then the glass forming ability is going to be higher, which means it is going to be easier to form a glass, and the glass that is formed is also going to be relatively stable. Again, when we say relatively stable, we do not mean that the glass or the amorphous form that is formed is going to be more stable than the crystalline form. What we mean is in the relative terms, that the amorphous form formed by class 3 materials is going to be more stable than the amorphous form that is formed by the class 1 materials. There is also a potential link, or there is a correlationship between the glass forming ability and glass stability. So the compounds that have a higher glass forming ability also give us a glass or the amorphous form which is relatively more stable. This property of the glass forming ability and glass stability helps us in identifying the need for using stabilizers for the amorphous state. What happens is that some of the APIs in their pure form would form amorphous form which is relatively stable, which means they can be marketed as pure amorphous APIs. There are some examples like cefuroxime acetyl, cefuroxime proxetyl, atorvastatin calcium, wherein the amorphous APIs are sold in their pure form for the formulation development purposes. While if the amorphous form that is formed for an API is not that stable, you will have to convert it into a amorphous solid dispersion by inclusion of a polymeric excipient, so that you are able to stabilize the amorphous form and hence use it for the formulation development purpose. So this is the significance of this entire exercise of determining the glass forming ability and the glass stability. We have discussed this number of times that the amorphous materials are physically less stable and will tend to crystallize over time under stress of temperature, relative humidity, etc. So this is the PXRD of the amorphous sample, which is a halo pattern, which upon storage, especially in presence of moisture, will tend to convert back to a crystalline form, which will then show the characteristics peaks of the crystalline form. This is the general tendency amongst the amorphous APIs. Some of the samples, as I told, may not convert to the crystalline state because they are relatively stable in their amorphous form, while the other samples may show this conversion from amorphous to crystalline in a very fast manner. The factors that affect the stability of the amorphous form, or in other words, its conversion from the amorphous to the crystalline, are listed out here. There are several thermodynamic factors which are responsible for this particular conversion. So these factors are called as the configurational thermodynamic properties. Whenever there is a term configurational attached in front of the thermodynamic property, we are talking of the differences in thermodynamic properties of enthalpy, entropy, and free energy of the amorphous and the crystalline materials. Their values are obtained from configurational heat capacity data, which means we can calculate the configurational thermodynamic properties of any amorphous form using the configurational heat capacity data, which can be captured using the differential scanning calorimetry. Larger the configurational values, greater are the differences between the crystalline and the amorphous form of a material. And there are three configurational thermodynamic parameters that are governing the conversion of the amorphous form to the crystalline form. The first one is the configurational enthalpy, which is abbreviated like H and CONF in the subscript. Configurational enthalpy determines the enthalpic driving force for crystallization, and as a consequence, materials which show large values of configurational enthalpy should show a higher tendency of recrystallization. This also means that the differences in the enthalpy of the amorphous form and the crystalline form are going to be higher. That is why there is going to be a greater tendency of conversion of that amorphous form into the crystalline form. The next thermodynamic parameter is the configurational entropy, which indicates the entropic barrier of recrystallization. For materials with a high value, this indicates high structural diversity of the amorphous and the crystalline states. Higher the entropic barrier, the more difficult it is for the molecules to arrange itself in correct conformation required for recrystallization. In other words, it means if the configurational entropy is higher, which means the difference between the entropy of the amorphous form and the crystalline form is higher, the tendency towards recrystallization is going to be lower, because the higher configurational entropy means that the amorphous form can acquire a lot of different conformationals in the three-dimensional space, and if larger the number of these conformations, the more difficult it would be to acquire the optimal configuration for crystallization to take place. The third parameter is called as the configurational free energy, which denotes the overall thermodynamic force for crystallization from the amorphous form, and it is an outcome of both the configurational enthalpy and the configurational entropy. Moving over to the techniques for generation of the amorphous solids. For generation of the amorphous solid, the material has to be first energized, because we have to break down the intermolecular interactions that exist in the crystalline form. The next step is that the material is de-energized, and the third step involves kinetically trapping the amorphous form, and this is continuous with the second step. There are various methods that are used for the generation of the amorphous form. So here we have written what would be the starting material. So a crystalline material, if you do particle size reduction to an extent that the ordered structure is broken down, it will lead to the formation of the amorphous form. Another way of converting the crystalline solids that are especially solvates and hydrate is by the process of desolvation or dehydration. What happens is, when you remove these solvent molecules from the crystal structure, the structure collapses via solvent removal by exposure to modest temperatures, and you end up with a disordered structure, which is nothing but the amorphous form. Another way is starting from the solution of the API, which means you have dissolved the API in a particular solvent, and then you remove that solvent. And this removal can be done either by spray drying or by freeze drying, because these are two very common techniques. In fact, spray drying is more common as compared to freeze drying to convert the crystalline solid by dissolving it in a solvent and then removing the solvent suddenly to end up with the amorphous form. Another technique that is used for conversion of the solution containing a drug to the amorphous form is through rapid precipitation. You can either do it as a controlled supersaturation, avoiding crystallization, precipitating water soluble salt of a weak acid or base with addition of respective or a corresponding base or acid, which means this is a pH change approach. And then you can also use what is called as a anti-solvent approach. The molten crystalline material, when it's get into the liquid state, can be solidified suddenly to obtain the amorphous form. This technique is only useful in the lab setup, and it cannot be used at industrial scale. Another lab scale technique is to condense the vapors of the API to obtain the amorphous form. In terms of the industrial application, what we observe is that spray drying is one of the most common techniques to convert the amorphous form or to convert the crystalline form to the amorphous form. And another common technique would be the precipitation technique, which is sometimes used for conversion of the crystalline state to the amorphous state. Now here we are talking of techniques that are used for converting pure API from crystalline state to the amorphous state. We will be separately discussing the techniques that are used for the generation of amorphous solid dispersions, wherein spray drying and hot melt extrusion are the two most common techniques that are utilized. Some of the factors that affect the stability of the amorphous form, we have already discussed that moisture is one of the most prominent factors that affects the stability of the amorphous form. Let us try to understand how moisture affects the stability of the amorphous form. Water happens to have a very low glass transition temperature, and it has a TG value of minus 137 degrees Celsius, which is a very, very low value with respect to the TG. when water comes in contact with an amorphous API, the overall TG of the system decreases drastically because the TG of the water is minus 137 degrees Celsius. Since the TG reduces drastically, the temperature at which the molecular mobility will increase will also drastically reduce, because molecular mobility drastically increases when the material goes from the glassy state into the supercooled liquid state. So if this TG has decreased, so the temperature at which this change in molecular mobility will happen will also decrease. So this will make the material very prone to conversion into the crystalline form, and the stability of the amorphous form would be uh, compromised by the introduction of moisture content into the sample. There is a case study or an example that has been utilized here to explain this concept. So we have amorphous sucrose containing 0.5 to 5% amorphous content with 0.1% and 0.5% of moisture. So this particular set is when the moisture content is 0.1, and this set is when the moisture content is 0.5%. And this is the amount of amorphous material in percentage. So this is for 0.5% amorphous sucrose, which means only 0.5% is the amorphous sucrose, rest is the crystalline material. This is 1%, 2.5%, and 5%. Similarly, it is here for the same amount of the amorphous material. Then this is the moisture content in the amorphous zone, that is milligrams of water per 100 milligrams of the solid. So if you expose these samples to 0.1% moisture, means these samples to 0.1% moisture, these are the values of the moisture content that are picked up, and these are their respective glass transition temperatures. Now look at the values of the glass transition temperature as soon as you increase the moisture content or moisture amount from 0.1 to 0.5%. The value from 9 changes to minus 73. From 27 it changes to minus 36. From 45 it changes to 9. And from 49 degrees Celsius it changes to 27 degrees Celsius. So these are the changes in the value of the TG that happen because of the presence of moisture. So you can see the values drastically reduce because of the increase in the moisture content, and because of that the overall stability of the amorphous form is going to be reduced. Another important factor for the conversion is the temperature, and previous slide talked about the moisture content. This one talks only about the moisture content. So here we have shown certain samples, PXRD overlay of isothermal crystallization of amorphous itraconazole at 85 degrees Celsius. So the amorphous samples were exposed for different time durations to 85 degrees Celsius, and these are the PXRDs that are captured after these exposures. So at 0 minute the sample was obviously amorphous. At 60 minutes also it remains amorphous. At 65 minutes you can now see there is slight emergence of the crystalline peaks in the PXRD. At 70 it becomes slightly more prominent. At 80 it becomes even more prominent. Some new peaks have also emerged, and at 90 minutes you can see it starts taking the characteristic pattern of the crystalline sample, which means there is a conversion of the amorphous form into the crystalline form as the duration of storage at 85 degrees Celsius is progressively increased. The characterization techniques that are used for the amorphous systems are captured in this particular slide. So This way we have shown that the information that you obtain from the analytical tool is increasing in this direction, and the analysis time is decreasing in this direction, which means these techniques give you the maximum information, but they also give you or they also take the maximum time for the analysis. So the basic thermal technique, spectroscopic and diffraction techniques, they can be used as the first hand tools. They are rapid, but they give you very preliminary information. Then if you want to take more information regarding the phase compositions, you have to use DBS, that is dynamic vapor sorption, XRPD, solid state NMR, Raman spectroscopy and thermal analysis. So you can get more information, but the uh, extent of experimentation is going to be much more. Remember, some of the techniques are common with this particular set of tools, but the way you are going to devise the methodology, say for XRPD or for DSC, is going to be more elaborate in this particular set of studies. If you are interested in assessing the molecular arrangement, then you need to use Raman, IR, liquid and solid state NMR, XRD microscopy, XRD and microscopy to obtain molecular level information. And for the advanced level information, you can use various other tools like small angle X-ray diffraction, axis or wide angle X-ray diffraction, uh, pair distribution function using the XRD, NMR relaxometry, spectroscopy, and some other techniques are used for obtaining high level or advanced level information about the amorphous state. We end this particular lecture here. That was the last slide which we took. And we will now be moving over to a very important topic related to the amorphous state, which is the amorphous solid dispersions. Amorphous solid dispersions are the enabling technologies that are used in the pharmaceutical development to exploit the advantages of the amorphous form with respect to their higher solubility and subsequent higher bioavailability. We shall be taking that particular topic in probably next 2 lectures, and we are going to stop at this place for this particular lecture. And as usual, I look forward to your questions on the WhatsApp group. See you till we meet in the next lecture.